Okay, so now we turn to another major topic, parallel transport, covariant differentiation, and the Gauss Bonnet Theorem, major development in the theory. Well, we've introduced parallel transport and covariant differentiation in the context of a spherical geometry, but now it's time to do things with more generality, and to turn to a derivation of Gauss Bonnet Theorem, which is rather general. Okay. So a parallel transport. Well, we need a new concept of parallelism for a curved space. We all know what parallel means in the case of Euclidean geometry, but Euclidean geometry is simple because it has just a global concept of parallelism with the x-axis and the y-axis and no curvature by definition in the plane. So the direction x applies to every point on the surface of R2. Now, however, we have a curve. We have a curved space, and so the tangent planes to different points have different orientations, of course, and so we have a concept of parallelism that has to be generalized to such a situation, and that's what we'll be doing with parallel transport and covariant differentiation. Well, once we've done that, then we'll know how to measure angles around global curves, because we'll understand how to measure angles off of parallel transported directions, and we'll be ready for the Gauss Bonnet Theorem. So let's remember, how do we differentiate and understand vector fields that are parallel to a surface? Okay, well we begin by putting a curve on the surface to give us a sense of position and direction. And then the covariant derivative, indicated with this capital D, is then just the projection of the ordinary derivative along the curve projected onto the tangent plane. So that's written down here, okay? So capital D of V is ordinary differentiation along the curve minus the projection of that ordinary differentiation off the normal. So I subtract its projection on the normal, which means, of course, I'm really projecting it down into the tangent plane. Okay. So this is the differentiation that would matter to a being that was living on the surface. He's sensitive to the tangent plane, not to the normal plane, and so if he sees the vector changing along the curve, he means that it's changing in the tangent plane. For example, if the covariant derivative is equal to 0, and V does not change in the tangent plane in that direction, along that curve, and we say that V is parallel transported along R. So parallel transport is then just a simple special case of the covariant derivative. We've seen other examples. For example, we let V be the tangent to a great circle on the sphere, just dr by ds, where s is arc length of the great circle, and then the covariant derivative of that is equal to 0. Well, we showed that on the sphere. Okay, as you move along a great circle on the sphere, the tangent to the great circle only changes in the normal direction. Okay, and so its covariant derivative is equal to 0. The great circle is a geodesic. It's as straight as possible for a curve to be that's embedded in the sphere. Okay, it has no curvature to the left or to the right. Its only curvature is in the normal direction, kappa sub n, as we've discussed. Okay. So here I just remind you a little bit about that. If the covariant derivative of the tangent to the curve is equal to 0, then the curve is a geodesic. And I just remind you that that's the situation where R double prime, okay, where R double prime, the primes meaning differentiation with respect to S, is normal to the surface. So here I imagine a curve here, C labeled here. Okay, it has some curvature. The curve is in the surface, but its curvature could point in any direction in R3, and I'm imagining it's pointing like this, kappa little n hat, and that has a projection against the normal and a projection into the tangent plane. The projection into the tangent plane is what we've defined as the geodesic curvature, okay, and the projection of the curvature in the normal directions is kappa n, and we've seen that that's the basis of the second fundamental form, indicating how the surface is embedded into R3. The geodesic curvature is intrinsic to the curve. We'll show that explicitly in our developments soon. Although intuitively that's certainly pretty clear, and it plays a different role. And for example, if kappa g is equal to 0, then that curve is as straight as it possibly can be, and be embedded in the surface, and so that's a geodesic. And I'll just remind you of that stuff here. We read off from this triangle that kappa squared is kappa geodesic squared plus kappa normal squared. Okay, and there you go. Oh, and then I remind us, for example, about straight lines on planes, cones and cylinders. Okay, well, straight lines on a plane, okay, they're geodesics, of course. On a cone and a cylinder, cones and cylinders are related to R2, to the plane, just by bending, okay, and so they share the same straight lines, okay, okay, and for example, on a cylinder, okay, the circle around the cylinder is a geodesic, okay, and I see that just by unfolding the cylinder and seeing that when it's unfolded, it's that curve is simply a straight line. Okay. So we discuss these things in the books, and we make the distinction between local paths of minimum distance and global geodesics. You have to be careful about some of these ideas, and we do that in supplementary lecture 9. Show lots of examples, and then in the textbook as well. Parallel transport in a plane, of course, is the good old thing. Here I'm parallel transporting a vector called v of s along a curved path c. But you see they're always pointing in the same direction. Okay. Okay. So for example, that might always be in the northerly direction. I have a global sense of up. Okay. And so this might be along the y-axis, and so it maintains the direction toward the y-axis, even though c is curving around like that. So that fellow is parallel transported around. Here I'm just parallel transporting my pointer here. Okay, and it's that simple concept on a plane. Okay. If I was parallel transporting this fellow as a tangent vector on a sphere, of course, then it dips down, okay, and its r double prime is perpendicular to the sphere. Okay. Let's remember a few things about parallel transport on the plane. Well, on the plane, if we have two vectors which are parallel transported, they maintain their magnitudes and the angles between them. Okay. Well, that's pretty obvious. Okay, from Euclidean geometry, but this is also true for general parallel transport. And how do we prove that? Well, let's just take two vector fields v and w, and take the inner product of them. I'm on a general surface now. These fellows live in the tangent plane, and I differentiate them with respect to a parameter that labels perhaps the arc length along the curve. If I differentiate it, then of course I'll get two terms, okay, where v prime means just dv by dt, and then since this is a dot product between v prime and w that lives in the tangent plane, I can replace v prime by the covariant derivative of it. right? Because v prime and the covariant derivative just differ by a vector in the normal direction, which does not contribute to the dot product. Once I do that, okay, and then I say that my two vectors are parallel transported, these covariant derivatives are by definition 0, and so this is equal to 0. And again, I learn, okay, that the dot product of the two vectors is invariant to moving along the curve if the two vectors are parallel transported. Okay. Let's consider a less trivial example of parallel transport. I'm going to parallel transport a vector along a non-geodesic on the sphere. So I have in mind here, okay, a cap, what's called a cap, just a circle here on the sphere, okay, like that. It's not a geodesic. You see that the cap lies, of course, in a plane, and that plane does not intersect the origin. Okay, it intersects the sphere, but not the origin, so it's not a great circle. It's not the quickest way to get from one point to the other, if those points are close enough together. And then I might want to parallel transport a vector I call W0 around this path. Okay, it's on a curved surface, and it's a little bit challenging to visualize that. Can you transport W0 along C? Okay, it can't remain tangent to C because C is not a geodesic. I start off with it as a tangent, but as we parallel transport it around, it's not going to remain a tangent to the curve, because that would give us a contradiction. So where does it point? Okay. Well, here's a trick. Okay. If we put a cone over the cap, okay, then I can think of the movement of W naught on the cone. Okay, I place the cone so that the cone always corresponds to the tangent spaces to the cap C. Okay. Okay, and that's a good thing to do because the concept of parallel on the cone is a naive concept of parallel because it inherits it from the R2, from flat space in two dimensions. A cone is flat. It's just, you've just wrapped up a piece of paper, a flat piece of paper, into the shape of a cone as indicated here, and so then I can read off the movement of W naught as it moves parallel to this curve. Okay, so that's what I've done here. I've put a cone on top of my sphere, and then I unwrap it. Okay, and so now I know the answer, because once I unwrap my cone, I know that since W moves by parallel transport, and the concept of parallel transport on a cone, since a cone is flat, is just a naive one, a global parallelism. I know how it moves. So here it is at the beginning of the curve. Here it is halfway through. See, parallel. I've unfolded this cone, which is flat, laid it down on my poster board, and so W stays parallel to itself. Well, at the same time, the tangent to the curve rotates around, and if I rotate through an azimuthal angle phi, as shown here, then T, the tangent, will rotate through that angle because T has to remain perpendicular to the radii, as shown here. Look at the radii coming from the apex of the cone down to the curve C, as shown there. So I see that once I get to this point, an angle has opened up between W and the tangent. Okay, the tangent being the original direction of W, and that angle is simply phi. Right? So that then solves the problem of how to parallel transport a vector along the non-geodesic in this particular case. I was able to map the problem onto a conventional simple problem without curvature and solve it. Okay. in general, sometimes the differential equations for parallel transport, okay, and for geodesics are relatively complicated. I'm not emphasizing them here in this lecture system, but they're discussed in the textbook, and you can look at more general applications and illustrations there. I just feel that this one is quite a nice one. Okay, the fact that k is equal to 1 unit sphere for the unit sphere, and that C is not a geodesic are responsible for the appearance of this opening angle phi that opens between the original direction of the parallel transported vector and its original direction. Okay, so that's a good one. I wanted to do an illustration which is a little more challenging than the traditional ones, which always look at geodesics, and here's one that we can solve for very explicitly with simple geometry without getting lost in a second order differential equation for geodesics, and I find that one instructive. Okay. So now with parallelism, the idea of parallel transport, we're developing the idea of direction along the surface. Okay, and we can discuss the turning angle and generalize that concept from Euclidean space to curved space as well. Remember when we discussed the closed curves in Euclidean space, we had a turning angle. We related it to the curvature of the closed curve, and we could measure it and understand it as we move along a curve which might be simple and closed. So now let's discuss turning angle and see that the generalization of turning angle to a curved surface produces the Gauss Bonnet theorem. Okay, so that's what we'll do, and we begin with an observation to get us going. We begin with two vector fields V and W, and we suppose they're tangent to a general curved surface S. We suppose the cosine of phi of P is the cosine of the angle between them at the point P. Okay, and let V and W be normalized, so cosine of phi is just the dot product. Okay. And now let's imagine calculating the covariant derivatives of V and W, and we want to observe that the difference of the magnitudes of the covariant derivatives is nothing but the rate of change of phi. Okay, so I can measure the rate of change of phi by doing these two calculations within the tangent planes and taking the difference. Okay, and that's the rate at which the angle between the two vectors might change. Okay, what do I mean by this bracket? That just means the algebraic value of. Okay, because if I take a covariant derivative, it has a magnitude and a direction, and I'm just taking that direction off, that unit direction off. Well, how do I derive this? Well, it's pretty easy actually. I just followed my example that I did before in the special case of parallel transported vectors, and differentiate the statement. Okay. So I'm going to differentiate this equation 1. Okay. So I differentiate it along a curve R of t, and so it appears like this. Again, as soon as I see a v prime, I can replace a v prime and a w prime by the covariant derivatives, because the dot product makes a projection back to the tangent plane. Okay, and the covariant derivative and the ordinary derivative have the same components within the tangent plane. Okay, so that's what I've done here. Okay, and then on the right hand side, I just have to differentiate the cosine of phi with respect to t, and that gives me minus sine of phi d phi by dt, and that's what I'm interested in. Okay, so I've made some progress here. I see I see the covariant differentials, and I see rate of change of phi. So I'm in the right direction. But now what I want to do is I have to pass from the covariant derivatives to the magnitudes of the covariant derivative. So let's do that now. Okay. So here I'll just write that the covariant derivative of v is the magnitude of the covariant derivative times its direction. Okay. Well, what is its direction? Well, the covariant derivative lives in the tangent plane, so it's perpendicular to the normal. Okay. And it's also perpendicular to the original vector itself, right? That's it. The original vector was a unit vector, and if I differentiate it, then I know that the derivative of it is perpendicular to the vector itself, so that its length is maintained. Okay, so therefore I can write the direction. It's in the direction of n hat cross v hat. Okay, that just gives you the right direction for the covariant derivative. And all of the guts of the calculation are then hidden in the magnitude like that. The direction is easy to surmise, so I can write it like that. And I can do the same thing for w. Okay, well that's good. What I'm interested in here is I see in my expression up here this combination of dot products, and so let's take those dot products, and that's what's done here. Okay, I'm doing the first term, and I write in for my direction for the covariant derivative, and I pull out the magnitude of the covariant derivative. I get that. And then similarly, I do the same thing on the second term. Okay, well now here I have to do a little bit of juggling here, because for the first term I have the dot product of n cross v quantity dotted into w. In the second term, when I'm doing the covariant derivative of w, I have the cross product of n with w and dotted into v. Okay, but look, this is just a simple scalar product, and one of the identities you know from vector calculus, okay, is that you can move the vectors around, and the only thing that changes is the sign. So I can check that I can cycle w to v and v to w, and the only thing that changes is the sign. Okay, it's just an identity of a triple dot product. Okay, so then if I do that, you see, now I can factor out the directions from the magnitudes in my expression and get what I want. Here's the left-hand side of the expression I'm interested in, up here. Okay, and now I use these, I just substitute in these identities, so then I collect a difference between the magnitudes and a common direction. And look at this direction. Okay, look at this direction. It's n cross v dotted into w. I know that the dot product of v and w is cosine of phi, and then I can ask, well, what direction is n cross v in? Okay, so n is normal. V might be in this direction. N cross v is 90 degrees counterclockwise to v. Okay, it's just v rotated by 90 degrees, and that's what I've written down here. And we'll see these expressions coming and going. So I'm giving it a name, r sub pi over 2 of v. It's just v rotated by 90 degrees. Then I can take the dot product between all these unit vectors. Okay, the dot product of the rotation of v through 90 degrees dotted into w. Well, the angle between v and w was phi, and so the angle now between the rotated v and w is phi plus pi over 2. I need the cosine of that. That's minus sine of phi. And that's what I've written down here. Okay, so now we're done, because here I have this expression, and I have this expression here. Okay, and so I see that they are they match if the difference of the magnitudes of the covariant derivative match d phi by dt. The sign is common between them and cancels out. Okay. In the case phi equals 0, you might worry about these things being 0, but you take the case phi equals 0 as a limit of non-zero phi, and so you have the identity for all phi. so comparing the last expression with equation 2, I derive equation the equation that I want, which is written right here, and it's a step in the direction that I want for the Gauss Bonnet theorem. In particular, okay, here it is. Let's apply it. Let's choose particular W's and V's to move toward the result I'm interested in. I take the special case of W being tangent to the curve, okay, and I take V to be a parallel transported field. So it gives me the sense of direction, okay. So dV ds is 0, okay, and substituting this into the previous equation with dV ds equals 0, one of the terms disappear. The other term is just the covariant derivative of the tangent to the curve, and it's the magnitude of that. And remember what that means, right? That's just the geodesic curvature, right? That's just the geodesic curvature. This is just the projection of the acceleration of the curve C onto the tangent plane. That's kappa sub g. And I learned therefore that kappa sub g is the rate of change of phi, where phi is the angle between the tangent and the parallel transported vector v. Okay, so the parallel transported vector v is replacing the stationary x direction, say, in the illustration that we did in Euclidean geometry. Okay, now I have the generalization of that expression to the case where I have tangent planes which change direction as I move along the curve. Okay, kappa sub g is given by the rate of change of a turning angle, but the turning angle has to be defined appropriately. So it's the angle off a parallel transported vector v and the tangent itself. Okay, so I mean that's the concept behind this, and I think it's a very clever observation. Okay, and so I point those things out. Okay, I point those things out now. So armed with this result and the other general result, we're ready to discuss the Gauss Bonnet theorem, and we'll do that next time.